think more about machine learning. We all are the best in it. So quantum machine learning essentially tries to build machine learning models in quantum computer. So what we have in classical computer or whatever models that you build right now, it is basically, it's more or less based on how classical computer works, and we're trying to see, can we adapt those techniques to quantum computing and build machine learning models which can run on quantum computer. And that is where we look with, that's what we look at today, that is quantum machine learning. And just like any other machine learning models out there, it has tons of applications, starting from classification to generation of data set, generation of images, generation of all those things that we are looking at right now. So to give a motivation about why we need quantum machine learning, it's important to know what is the current gap that we are seeing. You can probably tell me more about that. This is what I could understand is there is exponential amount of data. It is not like in the old days where the data was scarce. Right now, because of digital explosion, there is huge amount of data that is available, and there needs huge amount of computing power to essentially deal with this data. And that is where I think one of the biggest motivation comes in. Second one is that still a lot of machine learning models right now are unable to learn complex patterns. If it is linear or otherwise, it will be able to learn much more easily. But if there is much more complex patterns involved, it might take more time and computing power. And another important problem, as we all know, is the amount of computing resources that current machine learning models takes up. Because to train like a model like GPT, I don't know how much it is have taken the rail number, but it is a huge resource that is already being used. And is there a way to actually reduce this? So these are the motivations, or these are the problems that we are trying to see that QML can solve for us. Of course, right now yes, but in future it will become much cheaper. That is going to be the way forward, because as you might know, initially the classical systems that they were built were ENIAC, which is one big house, one big room. So they would have cost a lot, and that is in the similar state that we are now. It will of course cost a lot, but once we go forward, once we are able to actually make it to a compatible module size, it is of course be much more comparable to other GPUs right now. And in the place where we require probably, let's say 10 or 20 GPUs, we might only require one QPU. That is the hopeful comparison that we can have. Now, just to recap the things that we studied and looked at in the last session, we can exploit the quantum phenomenons out there, like quantum superposition and quantum entanglement, to build novel quantum algorithms, and this hopefully will give us a quantum speedup, because as we discussed last time, there is going to be a huge amount of speed up that we'll get essentially with a good quantum computer. And we can also look at innovative quantum algorithms, not just the current machine learning algorithms, but also different types of innovative algorithms, which will help us to look at the search space, as we say, the number of solutions that we need to find in a much better and easier way. And also look at hybrid approaches. where we not just look at quantum algorithms, but also combine them with the algorithms that we already know. They are the classical ones. So combine both of them and get the best of the both worlds. So this is basically the premises that we are building quantum machine learning algorithm. We're trying to see if quantum phenomena can help us in any ways, and also try to bring both classical and quantum phenomena together to make a better algorithm. To give a quick introduction, most of the applications is very much similar to all the applications that you do right now in machine learning. There is nothing different in it. So pharmaceuticals, finance, materials, energy, transportation, all of these industries have a lot of applications that you would have probably looking at. And just covering it up over here, nothing different from just the classical machine learning, but here we will be able to improve the cost efficient, the compute power, and also the speed. That is where we are looking, and we are motivated to do quantum machine learning. So this was just a general introduction of quantum machine learning, how we do, what we do, and why we do. We can combine best of both the worlds, and that is how most of the algorithms are being built. So algorithms right now are not just quantum algorithms. It is a combination of some part of quantum, some part of classical, and that is always going to be for some time, because the computers are not powerful enough to actually run something truly quantum and just quantum. And to motivate you to understand the architecture of a quantum machine learning algorithm, I've taken the most simple one, SVM, that is support vector machine, and the quantum version of SVM, that is quantum support vector machine. This sort of algorithms are best for classification and regression, binary classification, also multi-classification, also regression. They are good in this sort of task. And QSVM is also is actually showing a lot of potential in these areas right now. So what we essentially do in building a quantum machine learning algorithm is taking the essence of classical algorithms, classical machine learning algorithm as it is, and trying to see which part of it can be improved by quantum. That is essentially what we do. We won't make all algorithm in quantum. We'll see each part and see which part can be improved by using quantum. And as we might know, the first part of support vector machine is actually coding all the data, or actually building a kernel matrix. There are multiple type of kernel matrix available: linear, SBF, then quadratic, a lot of them. So that is a part, that's the first part, and then we have an equation that is formed after building the quantum kernel, that is a loss function, and then we optimize for it. So this is how the simple SVM method looks like. Now what we do in quantum support vector machine is, it's no different than the classical support vector machine, but instead of a classical kernel, we put that in quantum kernel. We try to build a quantum kernel and get the data through it, and then perform the similar support vector machine evaluation. So the only change here is, instead of the classical kernel, we use quantum kernel and quantum functions to actually build that value. Now this is a key difference, but before going to that, there is also another important thing that you should definitely keep hold of. That is, I'll probably start with an example. So if I hope all of your mother tongue is Telugu, and if you're given an examination, let's say in Malayalam, examination question paper in Malayalam, even if you know the answers, you won't be able to answer anything, right? So that is a problem that we also face in quantum computer. All the things that is written, all the things that is in your classical machine or a laptop is in classical language, 10010, that is bits, right, classical bits. And there needs to be a translation of that classical language to quantum language for the quantum computer to understand. And that is essential, or else how much ever great your computer or your model would be, your model will fail. That is going to happen, and that is where what we call quantum feature map, as you can see here, quantum feature map comes into place. Quantum feature maps, or we call it encoding, quantum encoding, or quantum feature map, these two are the main terms for them, are essentially translators. You can call them as translators, which translates the information from classical computer, classical language to quantum language that a quantum computer can understand. And it is also very important part of QSVM algorithms, QML algorithms. So quantum feature map, then we have quantum kernel. Once you build the quantum kernel, it is similar SVM. Then we do this SVM, simple SVM technique, and you get the results, and then you do comparative analysis. You can also have data pre-processing before even building the quantum kernel. We usually do that. All of machine learning models does quantum pre-processing before to actually get into this. And there are different studies that shows that some bit of pre-processing will actually help to improve the results of quantum machine learning algorithms like QSVM. So data pre-processing also an essential part of SVM and QSVM. Now the main advantages of this is, as I've told you before, smaller search space, and also adding to that, of course right now there is huge number of challenges out there. As I discussed in the earlier session, there are huge quantum hardware limitations. Right now noise is a huge problem, and there requires a lot of error and mitigation techniques, and also there is a lack of good quantum machine learning algorithms. We have simple QSVMs and other things which is direct forward, but we need much more complex quantum machine learning algorithms to actually see some practical use cases. So I hope the QSVM part is simple. I haven't put any quantum language or quantum equations here, just to keep it simple so that you understand it is okay. It is similar to another machine learning model. There is nothing different. It is similar to another machine learning model. The only thing is that you need to understand two more things. That is a feature map, quantum feature map, probably that you need to understand, or quantum kernel. Most of them uses a similar kernel. You don't have multiple kernels. That is the most important thing about quantum support vector machines. So only thing that is extra in support vector machine, other in the classical, in quantum is quantum feature map. And the rest of the thing is actually pretty much similar. You can easily do all your simple, similar, whatever machine learning algorithms you have been doing in classification in quantum support vector machines also, because it is as simple as support vector machines. Now there is actually different QML algorithms that is out there, not just QSVM. There are algorithms for quantum neural networks, which is similar to quantum which is similar to neural networks, but have a very slight twist. We have, instead of having a layer of neurons, classical neurons, we can have a layer of quantum neurons. It's simple. You can have layer of quantum neurons plus classical neurons and add up and make a neural network layer. And decision trees, it is much more involved. Going to that into depth will be won't be possible here. And quantum generative adversarial networks, they are also easy for you to understand. You build two machine learning models, that is neural network models, one as generator and one as classifier. I hope everybody knows GANs, generative adversarial networks. So if you have generative adversarial networks, GANs, there is one neural network which is called a generator, and another neural network that is called a classifier. And what we can essentially do is to actually make the generator as a quantum generator, quantum neural network layer, and the classifier as a simple classical neural network layer. And this is another interesting algorithm that we have. And we can also have quantum reinforcement learning. Again, it is a bit more advanced. There is also QNLP, quantum natural language processing. Again, that is also a bit advanced. It is not direct forward, as I've said before, about taking one part into quantum. The architecture of QNLP is fundamentally quantum. It is not going to be direct forward. It is much more involved. So this is the part that I want to discuss about QML and give a small introduction. And also, most of you would have seen this, found this very much difficult to comprehend and also code for it. And that is where what I am currently building currently is what we are building is block, where you can build any quantum algorithms of your choice with simple inputs. As you can see here, if we want to build a machine learning algorithm, you can give whichever feature map that you want. There are multiple feature maps available, so you can describe which feature maps you want. You can upload your own data set, and also you can set number of qubits you want, the depth of it, and also which device you want to run it on, and it automatically codes for you and deploy the circuit, and you can actually focus on the results and improving the circuits without worrying about the code part. So this is something which is in beta stage, and I haven't shared it with anyone, so this is the first place I'm sharing, and I'll be glad to share our tool with all of you once we are ready. So thank you. So we'll probably release this within 1 or 2 months. We have a simple beta worked up ready, and so you can also scan this code to fill a simple form and get access to get early access, or else I'll share the link with Dr. Kalyani for her to share with you. But once our tool is ready, of course I will share the tool with Dr. Kalyani, so that you all can work around with and probably do something on your own, because this is something that I think will help you once we have the data input feature also. Right now we don't have that. Once you have data input, so you can bring any of your data, and just like you do any other classical machine learning, you can do quantum machine learning also. So this is a bit small introduction about QSVM, QML. I haven't went into depth of any of it because I don't want to scare in its very starting stage. And if you want, we can start with quantum programming. I think that's why we are at the lab here. Or else.
Can we have an application of quantum QSVM or something like that?
Yeah, so I have a.
As you said, kernel can be built with quantum, and the remaining classifier is the normal.
Exactly, yeah.
Can you just show that?
Sure. I'll. So I'll walk through the code, I'll walk through the program, because there are a lot of libraries involved, there are a lot of functions involved, so it will be difficult, but I'll try to walk through the program, try to give you an understanding about which part defines the things.
Like when we want to work on those QML algorithms, I just want to have a glance on your application.
Sure. So
maybe that will become a demo for us.
Okay, so I'll probably show you another. So this is a demo application. This one is a demo application. It's not on a real data set, but I have other programs which is on real data set. I can also show you that. So similar to any other quantum algorithm, you build a quantum circuit, as I've told you. First thing is building a quantum circuit and putting that there. So quantum circuit, that's the first part. Then you install quantum machine learning, which is a great feature that you already have quantum machine learning module in Qiskit. So we have this Qiskit machine learning, is available. So the rest of the part is basically, this part is where we build a simple data set. This part is where we try to build a demo data set. So the data set is something like this, where we have random numbers and random classifiers, A, B classifiers. So just random classification task. I think this will be the most interesting part. This part is where we define the feature map. I hope it is clear where we define the feature map. So there are multiple feature maps available. I can probably name few: Z set feature map, Z feature map. Then we have poly set feature map. Then we have auto feature maps. Then other feature map that probably I want to learn in depth. So you can define multiple feature maps, and what you do is essentially put your data. This is the data that we have been created here. So this is the data that we have created, and you input that data to the feature map. Essentially, you are translating it.
What is the data?
So data is a simple it's a simple 20 data points, random data set that we have created. So features, 2 features. Yeah. So nothing but nothing much into it. It's simple, where you most simplest classical machine learning task. This is so I'll probably go into practical application later. This is a simple data set which is randomly generated. This is randomly generated. 2 features, random numbers, random entries to all of these things. I can probably explain in a numerical features. No categorical, all numerical, nothing different. It's very simple data set.
What is our objective now?
To classify it into A or B class. There are 2 classes basically, A, B. We need to classify it to A or B. So you can see the spread of each data points. So A class, B class. We have split into train and test. This is basically it, and we need to classify it into A and B. So very simple classification, 2 labels. It's a demo, that's why. So we have this ZZ feature map where we encode the data into this particular feature map, this quantum language, so that quantum can understand. Then we have quantum kernel. Then what we build is quantum kernel. So here we build quantum kernel using so if you remember, there is multiple type of classical kernel. There is linear, quadratic, SBF and others, right? If I'm correct. So similar to that, fidelity is the mathematics behind building this quantum kernel. It's like linear. There is a mathematical formulation called finding fidelity. That is what we'll use to calculate our quantum kernel. So these are the 2 different steps other than the SVM steps. The rest is simple and straightforward. You first translate to quantum feature map, and then you make a quantum kernel. So this is the quantum kernel that we have made using fidelity quantum kernel. There are other types of quantum kernel available, but we use mostly fidelity. And as you can see here, this is just defining which type of mathematics you use, like linear or quadratic in terms of machine learning, classical machine learning. And this is simply the feature map. This is simply the feature map that we have defined here. So everything is straightforward, and then the rest of the things is simple SVC. Look at it, SVC. Then we say, okay, evaluate this kernel, and then you fit it. Then you fit train features, train labels. Then you look at the classification code, test score. This is train labels, and also find the final test score. So this is simple and qubits will come at this point. ZZ feature map. So I'll probably show you. ZZ feature map is essentially a circuit. ZZ feature map is essentially a quantum circuit that is already being built. So this is the feature map. So this is the inserted feature map quantum circuit. So what we do here is if you can see x0, x1, x2, right? If you can see that clearly, x0, x1, x2 are our input or our data. So in our data it will be 1, 2, 3. You input that and you will get this circuit, and this is what's the starting point. And this is the starting point of our QSVM. Then you create a quantum kernel. That will be a simple number. That will be some mathematical number and vector. Then you do the simple SVM afterwards.
Just expand a bit regarding, like you said, two features are there considered. So those two features, how they are going to be given as an input, and how this kernel is formed. Like, can I have it?
Yeah. So essentially, if you have two features, you need of 2 qubits. 2 features to encode unit of 2 qubits. So all the entries, all the data in that one feature, let's say the data is age, then 20, 30, 40, 50 will be the entries. That you can input as x of 0, that is the first feature map number, and that's essentially a computation inside it, probably. So essentially what you need to understand is all that vector, right? So if you have do you have a marker?
So one feature is considered as one vector. One feature
Yeah.
is encoded as one vector.
And then can probably show you the equation also here. I'm unable to find the
The regression also we will use it different.
yeah, you can use quantum for regression also.
Classification.
Yeah. No. We can use for regression. Yeah, prediction also we can use. So neural networks can be good for regression in that terms.
Still we are in just autoencoders in deep learning, and quantum autoencoders are come, quantum GAN has come.
Yeah, all of them are there right now.
Looking for advancement.
So I think I can also share this, but there was a nice documentation from IBM on quantum machine learning. So again, this will all will seem different, at different places, right? Quantum feature maps. So IBM had a very nice write-up on quantum feature map. Penlane is from a quantum computing startup called Xanadu. So they are a Canadian-based company. So they have developed Penlane. Okay, so can I get the mark?
I just need a small demo of how we could give a data set to a quantum.
Okay, that I'll show you here.
So that we could work on our own data sets.
That I'll probably show
Like
you.
suppose we have ID's data set classification. So ID's data set classification will be having 3 different parameters of settle length, settle width, petal width and all, right? So, and that is going to classify.
Exactly. So here I'll try to show. This is on credit card fraud detection dataset.
Okay.
Credit card fraud detection. It has 20 features, and all the features are actually PCA. They are transformed using PCA, so we don't know what are the features, but it has 20 features. And what essentially you can do, all these are actually QML code that we wrote by hand to improve the Qiskit itself. So yeah, so this is a data set. So as you can see, this is a data set V1, V2, V3. There are 28 data set, 28 features. 28 features you can see here, and
All that data is, what is the description of the data?
so this we don't know because it is PCA transform. It is a very confidential data set. So we know time and money is there, but rest we don't know. It will be probably name, time, place, and credit card, financial transaction data set. So it's a very confidential data set. Now, wait a second. Can probably find the place where we defined. Okay, it's not here. So essentially, you can see here, right? We have defined the data set. We have found our own data set, and similar to what we have done initially, I can show it here, right? You have taken the data set and put it over here in a feature map, and you define the feature map, and then you transform it. Yeah. So essentially, how feature map works is, what is that? So feature maps are nothing but circuits, quantum circuits, and what they does is, here there is only 3 features. As you can see, only 3 features. That is essentially, if you take it as a vector for each of the data points. Let's say we have person 1, age, income, and height. This will be 1, 2, 3, some random number similar to 3, 2, 1. So x0 is this, x1 is this, and x2 is this, and phi is actually a complex complex equation or a formula. It goes something like e raised to I something. So it's a complex formula. We don't want to study that in depth. So then what we do, we have these numbers over here, all these numbers over here, to convert this into a quantum state or a quantum into a qubit. So that is how we encode these states into our qubit state. Here you can see there is this phi, right? Phi is a function. It's a function. It's a function of what you give, and then you have something like u1. If you can see, u1 is there. So they are gates, nothing but gates. So what it essentially does is it takes the data that we have and it try to encode it into a gate so that it can be acted on a qubit, and then it continues from there. And this is how we do quantum encoding, or this is how we try to start our quantum machine learning process. So we don't want to actually go into much depth here, because quantum feature maps are very much technical. It involves functions like u1, which is a gate that it's going to be difficult to learn. We know x, y, z gate, they are very straightforward. u1 is a gate that is very difficult to learn, and phi is another function which is be a bit difficult to understand, because it involves something called complex numbers. So that is also another thing. But essentially what we need to understand is, you give a classical data, whatever data you have, you give that to the feature map, and that is enough. And you can play around with different feature maps. As you can see here, this is as you can see, this is one of the labels or one of the inputs of block. You can also change the qubit. So it essentially tries to bring this complex and complicated procedure into a much more easy and much more easier to understand way. So it's a humble effort to do this. So, as I've told, the only difference in SVM is we are computing a quantum kernel using a quantum feature map, multiple feature maps available, and you can play around with the feature maps and then try to build a quantum kernel and do the SVC as you will do for any other data set. So SVC is very straightforward. You can do without much quantum knowledge, and also it won't be much difficult to learn. So I think this we can sum up QML, and probably if you want we can try to do a simple circuit on your own, as we have access to labs now. We can try to start looking into quantum IBM, the portal that I've suggested. Try to make a Gmail, try to make a Google account. So try to make a Google account in this platform quantum.ibm.com, and if you know, let me know if you have any doubt in creating a account in this platform, and then we can try to play around with the lab and composer platforms. So you should search for quantum IBM or IBM quantum. You will find this web page, and then you can start working on it. Yeah, we can. So you can log into quantum.ibm.com and create an account. Yeah. No,
Can I
no.
access from there?
You won't be able to. So you can search for IBM Quantum, and the second, most probably the second link where it's called IBM Quantum Platform. Okay, search for IBM Quantum, and you will find most probably second or third link called Quantum, IBM Quantum Platform. And it will be probably asking for you to register. So you need to register using a Gmail ID or any other preferable sign-in options. So once you sign in, you'll be able to see a dashboard like this. I hope you were able to log into this platform. So are you able to log in to the system, the platform? So once you're logged in, then you can go to Quantum Composer, which is the best way. I think you would have probably started working on it. And this is a place where you'll find the Qiskit code, all these things, direct forward, and you can use it easily. So here probably I can so gates, you can understand how they behave, and other things. We'll try to see for a gate that is bit unconventional, that is impossible for you to find in other situations. 0, 1. So this, so okay, you log into tokens. Yeah, so this gate called RC gate, which is something that you will have no similarities in a classical or classical computing. It is called a rotation gate. So as you can rotate them according to your wish. So you can rotate them through different angles. And here if you rotate them, let's say instead of pi by 2, by pi by 4, so you'll be able to wait a second. Yeah, so you'll be able to see different types of possibilities coming out. Delete this. So RC pi by 4. So we can try to rotate it pi by 2 and see. Pi by 2, let's rotate it by pi. Okay, wait a second. And also we have Rx gate, Ry gate, which are essentially rotations along x, y, z and axis. So we have for a sphere x axis, y axis and z axis. So if we try to rotate using x axis, it will come into one particular place. Y axis will come to another place. So this is something that is also immensely powerful, because we can have gates which are variable. We can have gates according to our own wish, with inputs that you can provide, rather than fixed gate like NAND, and OR and other things. You can have gates according to your own choice with different angles and different phases. So that is something that I think it's only available in quantum computing. And before actually going into this gate and understanding, you should try to understand the mathematics behind it a bit, or else you'll get confused us in how it is not, why it is not happening, why is it happening, and other stuff. But to get a simple visualization, it's a good place to start. So once we have that, you can go to lab if you want to do much more calculation, coding on your own. Here, once you open, you will be looking at a table like this, and you can start with Python 3 kernel. And once it is connected, you will be able to see a interface like this, and you can also export other So I hope you are able to log into this quantum lab and start with the Qiskit kernel, and once in Qiskit kernel, try to see the libraries that is being imported and try to find what else is missing for us. So anybody needs helps while setting this up, this lab? So initial part is writing and importing the libraries that we need. We will start with quantum circuit, then AER, then execute, then quantum register and classical register. So they are the most important thing that you need to start with to write simple quantum circuits. And once that is being imported, you can actually start writing your own code of creating a quantum circuit for yourself. Right now we have shown a 2-qubit circuit. You can go with 1 or 3 to try it out. So first thing is once you import, once you start with the Python 3 kernel for Qiskit, you won't actually require to import many other libraries. All of the libraries will be already being imported. So you can simply add AER, quantum register and classical register circuit functions extra to be imported. So once you have imported all the libraries, we can start with defining the quantum register, which is simply the number of which is simply a collection of different collection of qubits that you need to start with. And once you have built this classical and quantum registers, you can start writing code for your circuit. So we usually define quantum circuit as QC. It's quantum circuit. So here we have defined our quantum circuit. Then once you define the quantum circuit, it is simply a way of adding different gates. So there is no other difficulties here. You can start adding gates of your own preference, like QC.H0. So you can add it to 0th qubit, and you can add QC dot, let's say, X to the first qubit. We have 2 qubits. Then QC dot CX to 0th and first qubit. So for 2 quantum circuits, for 2 qubit circuits, we need to have 2 qubit gates. We need to have 2 different settings. One is control and other is the qubit that is being acted upon. So if you have any doubt, Oh, probably I should zoom in a bit. Is it clear now? So we have, okay, yeah. So what I've written there is quantum circuit. What I've defined is a quantum circuit. So using the registers that I've created, I've made a quantum circuit called QC. according to your own preference. So 0 means first qubit, 1 means second qubit, we only have 2 qubits, and Cx is so once you have built a simple quantum circuit, then the next thing will be to measure it. So you can have QC dot measure C. So essentially we are trying to measure our circuit here, and that will come as the next layer. And then the next step will be probably for you to visualize it. So that is where you can draw the circuit. So this is a circuit that we have built, 1 H gate. So I think at least all of you should try this. Create your own gates, put whatever gates you want and in whatever order you want, and then try to create this simple quantum circuit and try to draw it out. So I hope all of you are able to draw a circuit, build a quantum circuit and actually draw it out or visualize it. Then the next one will be for you to define the backend that you need to run it on. Let us take S1 and S2, simulator 1 and simulator 2, where we have defined state vector simulator, first simulator, and second is quantum simulator. So you can define that also. Once it is defined, you can start executing the job. I'm just copying this from here because it's too lengthy. So you can call an execution a job or whatever preference you have. It is simply calling the function execute with the circuit that you have defined. I have defined circuit as QC and the simulator that you want. I have defined the simulator as S1. And the shorts I'll probably reduce it to 2024. The next thing will be to actually have the job monitor, so that we can see where the job is. Is it started, or is it running, or is it finished? The next thing will be to get the counts. So job is a dictionary. Job.result will give you the result section. There will be much more other things in the after once you have executed. Probably I can show that. So I've been defined execute over here. We need to add execute also here. Thank you. Okay, I don't know why it's taking time. So it is taking a bit of a time because my server crashed, but essentially what you can do is continue this export execute. Import execute. I think job monitor. Okay, job monitor we haven't imported, so we can import job monitor also. Job monitor is not essential if you are not running a QPU, so we can decide if you want to import job monitor or not. And then here okay. So I'll import job monitor also here. Now we can see the job status, which is useful. I've taken shorts as 2024. It's completely up to you to select how many shorts you want. So you can also see what all things you will get once you and now we can print the counts. So as you can see here, the counts has been, we have generated the counts. I hope we all are able to run a simple circuit on device of your own preference, with your own short preference, your own gate preference. Try it out and get a knack of writing the simple circuit code, visualizing it. Then you can also try to show the histogram. So this is the histogram that we got. It is 0, 1 and 1, 0 this much times. And if I change any of the circuit, let's say I change this to Y, the result is going to change. Any of the gate, the result is going to change. So essentially you can play around with the gates, can play around with the simulators. Okay, we can probably try different simulators now. Different simulator S2. So can start running from here. So there's a slight difference, as you can see, there's a slight difference. Initially it was 1000, but here there's a slight difference. So that is what I was saying. If you change the simulator, it is going to affect a bit. So this one gave you better results actually. It is supposed to be equal, it is supposed to be pretty much equal, but as you can see here, okay, it also again start to fluctuate, right? So if you do multiple times, it is going to get fluctuation. That is where the quantum uncertainty is there. You won't be able to get, you won't get the same number of counts every time you do a thing. So if you run it again, it is going to change. So if you run it again, it is going to change. So it is 1024,000. So this is essentially your first steps to build a quantum circuit, to build a simple, to run it on a simple simulator. And this is just the starting point. There are a lot of other things that we can do where there are much more advanced features, but again it will be a bit of confusing at the start. But once you understand the basics of quantum mechanics and the maths behind it, it will be easy for you to start with it and actually write a program on it. And if you want to write it on Qiskit itself, we have a lot of different available resources over here. I think you should definitely check this out. So you can go to learning.quantum.ibm. There you will be able to find a lot of different resources. I've shown this in the morning session also, but I'll try to show it again. So try to start with one of those algorithms, at least this one, and exploring quantum algorithms, probably start with the beginning. So here they will actually introduce to simple, what we call TOE algorithms, Deutsch algorithm, Deutsch-Josa algorithm, and other things. So it might get little technical, so I'll probably suggest you to start with basics of quantum information, where you will have much more easier understanding, like Qiskit examples, what is classical information, then multiple systems, which is essentially multiple qubits. And what will happen once you have more than one qubit. Then again this goes to quantum circuits. What is a circuit, what is inner products, what is few other quantum mechanical terms that you need to understand. Then entanglement. So you'll probably understand the program that we did earlier and find that what is entanglement is, and actually see entanglement in coding and in real life. So this is actually really great place to start, and all of the sessions are actually simple with very direct forward coding examples with simple explanation of each of the things. So if you go to quantum information, you can see what I meant by actually writing a state vector over here and examples of qubit states. So we only have seen one qubit state that I've shown. There are multiple qubit states that you can write. And what do you mean by measuring quantum states? So all these are very simple, and it comes with Qiskit examples, which is direct forward. You can see a lot of Qiskit examples here, and you can also write things and even code in parallel. So once you complete this simple 4 session, you'll be comfortable writing any quantum algorithms. You won't face much problems, and once you're comfortable with that, then you can go on and start with quantum machine learning with probably QSVM or any other algorithms of sort. So I hope you all were able to write a simple quantum circuit and run it on your own, run it on different devices, run it with different gates possible, and try to visualize them and see how it is changing. If you run multiple times, how it is actually giving different results. So that is actually one of the things that you won't see in classical computers. One simulator, it's the same simulator, multiple times you'll get multiple answers. So that is essentially how quantum behaves, right? There is probability. Yeah. So mostly we choose state vector simulator, which is the best simulator that we have right now. So yeah, we can go with that for most of the things, state vector simulator. But but selecting a quantum computer, no, as we see there is multiple quantum devices, that will be much more trickier. It needs thorough inspection and thorough understanding about all these hardware and how they are built. So yeah, so some of the systems will be good for optimization, some of the systems will be good for machine learning. So that way you can select different hardware that is available. Execute the last 2 cells. This one, right? So just before it was 1024 401, now it is 988. So that is what I was saying, every time you run, even with the same simulator, the result is going to be different. That is what is quantum, and that is how quantum uncertainty happens. So you won't be able to say, okay, I got one time 1000, next time you also get 1000. No, it is going to change. And this is where a lot of things, a lot of advantage is actually coming, this unpredictability and superposition that we have been seeing. So you can also select S2, and you can also try to reduce the number of shorts, let's say 10, and it will probably complete it much faster. So as you can see, there's a clear differentiation. 4, 6, it is actually, very much, you can't say it is equally distributed, it's an equal mixture. And this is why we need more number of shorts, or else you won't see that clear mixture. But if we increase to 100, you will see an equal mixture. So you can see 14 and 51, it is very close by, and it can be equal mixture. And what if it is just one? It will probably show one state. So it only shows one state. It's just one shot, it really shows one state. That is what it got in the first measurement. That's it. Now probably you can play around with this and see how it is going to improve and how it is going to increase. So if it is too short, how it is going to be. So this is where you can actually see the randomness of quantum mechanics. So here both the shorts resulted in 0, 1. Both the shorts resulted in 0, 1. So this is the probability, this is the unpredictability of quantum circuit and quantum computer that we are seeing. And if we introduce 3, probably one of it will be in, one of it is in 1 0 and others in 1 0. Here also we are unable to see it is an equal mixture. We can see, okay, it is like a 60% 0 1 and 30% 1 0, but it's not the case. And that is where we actually need to run it multiple times to get the real mixture or real sense of the state it is. So you can also see for 1 qubit, so that now you don't get, probably with 2 qubits there are 4 states possible, 0 1, 1 0, 1 1, 0 0. But with 1 qubit, only 2 states are possible, 0 and 1. Then there you can actually play around and understand this much more. Alongside with the learning in Qiskit, you can actually do this in side by side. So please let me know if you have any doubt in running this. We can try to conclude this by running more circuit of your own, and if you have any doubts on all the things that I've told today, you can ask me that also now. Sure. can easily understand quantum information, and from there you can understand other quantum algorithms. So once you understand quantum circuit, once you are comfortable executing any quantum circuit with any different backends, you can then go on and build quantum algorithms. There are different quantum algorithms that I haven't discussed, which is not machine learning based quantum algorithms. There are like Grover's algorithm, Simon's algorithm, Deutsch-Stosa. Then these three simple toy model like algorithms, which will help you understand quantum algorithms much more better.
So where are all these algorithms used? Like I just came across those algorithms which are available. So already they are built in, right?
Yeah, most of it is built in, but some of them you need to write the circuit for. For example, Grover's algorithm, like, it will be much more complex, but just like we have built a circuit here, you need to write a circuit for Grover's algorithm. So for QSVM,
For which application Grover's algorithm?
Grover's is for search. No, it is not a machine learning based algorithm. It's not a machine learning algorithm. It's a search algorithm. It is a search algorithm where you can search and find. It's actually for objects. Now, if you have, let's say, 10 countries, you need to find, let's say, one country out of it. Then you can find a huge speed up, a quadratic speed up in this search algorithm. So that is one type of algorithm that you can start with. Grover's is very famous, and Grover's, if you hear, you might think it is made by an American scientist, but it's an Indian scientist. His name is Love Grover. He is an IIT Delhi graduate. So it is an Indian scientist contribution, and also other algorithms called Simon-Bernstein algorithm. That's also a contribution from an Indian scientist. So a lot of Indian scientists have contributed to quantum information. Then we have another very famous scientist working at I think IIT Hyderabad, who have developed a theory called no deletion quantum theory. It's very famous. So he's also an Indian. So a lot of Indian contributions are there. So I digressed a bit, but here you can see all the algorithms. Here itself you will be able to study quantum information, the first part, then fundamentals of quantum algorithms, the second part, where you will be probably able to study. So these are the algorithms that I've told: Deutsch algorithm, Deutsch-Stosa algorithm, then other type of, then we have Grover's algorithm, as I've told you. So this is for unstructured search, and the implementation is where you build a quantum circuit. So it's also just a quantum circuit you need to build and implement. Yes, it is available. It is available. Everything is actually available. QGAN is also available. I don't know where they have moved. So earlier it was called IBM textbook. Now it is called Quantum Learning IBM. Now they have actually moved a lot of these resources somewhere else. So, but I have those links.
Please do share.
I hopefully have those links, and if they haven't scrapped it, probably you can see it, or else I don't know. Right now they only have very few quantum information learning courses.
If at all they are not available, you can share whatever notebooks you have with you.
Sure. So that,
share it to participants.
Sure, we can do that, yeah. I'm unable to find machine learning. So there was a very nice textbook on machine learning. It was really interesting, it was really straightforward, but it is not available right now. But I'll try to find it out and share with you.
So since it's used for CNN, quantum CNN and all, then can we expect that in deep learning also? Like quantum is also in deep learning, right?
Yeah. So neural network is the starting point of deep learning, right? So
Quantum is
quantum neural network is already there, right? We have quantum neural networks. QNN is already there. We are getting good results with Q&A.
But we did not touch today. That's
Yeah, we haven't touched today. It is going to be so we have quantum neural networks. So we have, so for example, I don't know, so you have AlexNet and all these big neural networks, right? So similar to that, we also have different types of neural networks available for quantum. So earlier it was called tensor quantum neural network. Then right now we have another quantum neural network which is doing good. We worked on it. I can probably share if you want the code and everything. So we have worked on quantum neural network, quantum random forest. So one thing that I want to tell you all is this particular area, if you have really interest, if you have some interest, it's a place where you can publish a lot of papers, because research here in this space, it is very nascent, especially in India. Very few institutions are even aware about anything like this. So very little of them know quantum computing exists, and from that few of them knows quantum machine learning. So you can easily write multiple papers, publish it in good journals, and whatever result that we have, right, so it can be easily published, but we are unable to publish because it takes a lot of time for us. So we have implemented quantum machine learning on multiple different practical applications, be it credit card fraud detection. We also used in electricity theft detection, using recommendation system engines. So a lot of work we have done. So you can also start working on it, looking at your machine learning algorithms and try to make it into a quantum model. So this is the path that I have, and I'll be happy to help you if you have any more doubts.